solve the following differential equations by a series and by elementary method to verify the solution. Okay, so in this question I will do question number 1, and I will show you how to solve this differential equation using the series method. So the first step here is to assume, so I'm doing number 1. Okay, so the first step is to assume a solution of the form y equal series from n equals 0 to infinity of a n x to the n. Okay, so this is a power series of a general form, and I will assume that that's my solution for the differential equation, but of course with unknown coefficients a of n that I'm trying to determine in the course of the solution. So basically the challenge is to figure what those a_n's are. Okay, those are the missing n coefficients in the solution, and this is a first order differential equation, so I would expect to have one constant of integration. Therefore I would expect to be able to solve for all those coefficients in terms of one missing coefficient. Okay, the second step is to basically plug this in. However, if I plug it in, there's a y prime in there, so I'm supposed to first find what y prime is. So I'm gonna find y prime, so I differentiate this series, and these are the same rules of differentiation. An is constant and I bring the n down, so this becomes n x subtract 1 and minus 1. However, the only thing is when n is 0, the first constant is a number, because x to the 0 is 1. So when I differentiate that first term, it's going to get me 0. Therefore, after I have differentiated to infinity, I'm going to have one term that's 0, it's gone. So the number of terms will be 1 minus the original amount of terms. So I will lose one of the terms. So this will start from 1 to infinity now. Okay, so now I will take y and y prime and I would plug them in the differential equation. Xy prime equal xy plus 1, and so I will get, so let's do that. So I have x y prime is y is the power series general form plus okay. Now the objective is to, since I'm trying to put all these summations together, I need to do a few things so I'm able to do that. I am going to pull this x inside with this xn minus 1, and then same thing here, so I could have all the variables inside the summations. So this step here becomes n a n. So when I multiply these, I add the powers, so this becomes x to the n, and here I get n plus 1 stays the same.
Yeah, I'm a little stuck here. I don't know what's up.
And I'll pause here so I can answer my student's question. Okay, now I need to put these summations together so I can deal with them. The only problem is they don't start at the same place. So two of them start at n equals 0 and one of them starts at n equal 1. A further problem is that the powers of the x's are not the same. So the first step here after this is to make the powers of n the same. And the way I'm going to do that, I do that by changing the index. So I could go here and say, okay, I'm going to let here, so I can make this n equal 1, or n equal, to make n plus 1 n, I would say let k equals n plus 1. And then that means n has to equal k minus 1. So that means this summation here in the middle, to the right of the equal sign, becomes a, n is k minus 1, and this became x to the k. And now this is starting from n, which is k minus 1 equals 0, is the same thing as saying k equal 1 to infinity. Now here I don't do any changes because it's n equal k, so I would call n equal k and just simply change the dummy variable from n to k, but nothing else changes. K equals 0 to infinity. Okay, same for the one on the left. X, this is ready. K equal n equal k, so it stays the same. Okay, fair enough. So now all the x's have the same powers, x to the k. However, these series don't start in the same place. So there's 2 at k equal 1, 1 at k equals 0. So what I'm going to do here, I'm going to pull, so this is the same thing. When k equals 0, this is a0 x to the 0, which is 1. So I replace k with 0, plus the remaining terms, which now is a summation starting at k equal 1 to infinity. ak xk. And then this one stays the same. And this one is the same. Okay, now since all these series start at the same place, k equal 1, and they're all x to the k, I'm going to put them together. So I'm going to pull them into the same summation, and I'm going to, in the same step, so they all have x to the k, so I'm going to factor x to the k out. So then we get k equal 1 to infinity. The first one is k. Actually, they all have a to the k, so I'm also going to factor out a to the k x to the k. So this will give me k plus 1 plus 1. The last one is 1. These two are the same. So plus 1 is plus 2 ak xk plus this a0 here equals 0. Okay, oh, oops, wait 1 second, we made a mistake here. This is, I apologize, this is k minus 1. No, it's not the same. So let me take this back here. I just miswrote it, so because we changed to k minus 1. So I have, so if I factor out x to the k, I'm gonna factor out x to the k, and from the first one I have inside k ak plus ak minus 1 plus ak. Actually the second one is minus because I moved them to the left, so this is minus minus. I moved everything to the left or to the right depending on how you think of it. Minus a0 equals 0. Okay, so this is a polynomial because k is ranging from 1 to infinity, and this is equaling 0. What that means in algebra, that means the coefficient of each polynomial would be 0. or x would be 0. Now if x is 0, you know, this is a trivial solution. We would have a solution of y equals 0. This is trivial. That's not what we're looking for. We're looking for the other one, is when the coefficients are 0. So this is 0 and this is 0. So that means a0 equals 0. Okay. So I solved for the first coefficient, and I also have x or k, ak minus a k minus 1 minus ak equals 0. I could factor out ak, so this is k minus 1, ak equal a k minus 1. So that means ak is ak minus 1 over k minus 1. This is the recursion formula I'm looking for that would enable me to figure out the coefficients. So for example, k is starting at 1. So if k is 1, let's apply it for a few. When k is 1, I get a1 equal a0, which I know is 0, over 0, right? So this is undefined. This is 0 over 0. So that means this does not exist. Now let's start at k equal 2. So this is going to give me a2 equal a1, right, over 1. So that means a2 has to, so basically a1 is my unknown. This is my missing coefficient that I'm trying to find. This is basically the constant of integration for the first order differential equation. I do need initial conditions. Notice I can't mathematically, I need to have a physical situation to be able to solve for that. I can't mathematically figure out what a1 is. It's inherent to be an unknown in the differential equation itself. So I would need additional information to figure out what it is. So what I'm trying to do now is I'm trying to express everything in terms of this missing coefficient a1, which again acts as my c constant of integration in the equation, in the first order differential equation. Okay, now everything else can fall under that. So a2 has to equal a1, right? And then we could go to the next one. So k equal 3, and plug it in the recursion formula. a3 is equal to a2. Hold on 1 second. I have a feeling here something is off. X, ak. Yeah, so this would be a2 over so if k is 3, a2 over 2, right? And so a2 is a1, so this would be a1 over 2. Okay, and if k equal 4, I get a4 to be a3 over 3 minus 1. So now k is 4, so 3, and a3 is a1 over 2, so this becomes a1 over 3 times 2, or 2 times 3. Okay, now notice the pattern here. This is over 1, yeah? So so you could see, we can start to see a pattern here. This is 1, which is the same thing as 1 factorial. 2 is the same thing as 2 factorial, right? This here is the same thing as 3 factorial. So you can see what's going on. The next one will be 4 factorial. Let's check it out if this is indeed the case. If k is 5, plug it in the recursion formula, you're gonna get a5 equal a4 over 5 minus 1 is 4, and a4 is a1 over 2 times 3, so this is 2 times 3 times 4, which is equal to a1 over 4 factorial. Indeed, so we do have a consecutive integer of factorials in the denominator. So if I keep on going, right, when k equal n, I'm gonna get for an to be a1. Remember, all in terms of that missing coefficient a1 over, so this is the original minus 1, so this would be n minus 1 factorial, or k minus 1 factorial. Let's just do it, n minus 1 factorial. Okay, so now I have solved for all these coefficients in terms of a1. I could plug this back into the assumed solution, right? So my assumed solution is, so this is y equal the summation from n equals 0 to infinity, right? A1 times, so notice that this is going to be x to the n, right? So if n is 0, we're going to get 1 here, divided by n minus 1 factorial. Right, I could pull the a1 out if I need to, but that's basically what this is. Okay, there's many ways to write this, and you know, this would be an acceptable final answer. However, if I need to write this in a little bit more informative way, I could allow this to start at, so I would replace the n minus 1, okay, let me just do this in a slightly different way. I could say this is the same thing as a1x times x to the n minus 1, right? Because x times x to the n minus 1 would give me n minus 1 x to the n, and this is n minus 1 factorial for the purposes of making this and this the same, right? And this is from n equals 0 to infinity. And now I can relabel the index just like I did before, change the indices. So I would say let k equal n minus 1. And if I do this, then y becomes, so that means n is k plus 1. So so this is gonna become from k equal minus 1, but that wouldn't make any sense, right? So this is gonna start from k, we'll come to the starting and ending in a second. This would be a1, right, x times x to the k over k factorial, if you like. Okay, so this is just another way of relabeling that. And here, if k is 0, if k is 0, we got a1x, because 0 factorial is 1. So we could start this from 0 to infinity. Okay. But however, let me stick to this answer here, and now I'm gonna, so this would be my final, this would be my final answer. This is the solution for the first order differential equation in the form of a power series, right? So so let me continue here. So for example, when n equals 0, I would get 0 doesn't work, right? Because you get minus 1 factorial. But when n equal 1, you would get a1, which would make sense because we said that a0 is 0. So there's no term, this is what I was saying here, there is no term with constant coefficient. In other words, every term, because in the original solution here, I was able to see that a0 equals 0. So there's and this is the only constant in my series. So if this is 0, there shouldn't be any other constant. Now if if n equals 0, that would make x to the 0 1 would make another constant, which is not true. So that means n here would have to start at 1 for the reasons I just explained. And if n starts at 1, then this solves kind of the mystery here. That's why if n starts at 1, that means k starts at 0, because k is n minus 1, and that's why I wrote 0 here. Okay, anyways, going back to the red series, the red solution, this would be, if n is 1, we would get a1 times x over 0 factorial. So this is just x. I'm going to factor the a1 out. And if n is 2, this is going to become 1 over 1 x squared, right? And now we're going to go to 1 over 3. If n is 3, this is going to become 2 factorial. So this is 1 factorial. This here is 0 factorial, because that's 1 x cubed, etc. So this is going to be 1 over 3 factorial x to the 4, etc. Okay, so this would be my solution. So this is just another way to write it. Okay, now let me solve that differential equation using elementary way of solving this first order differential equation, which is xy prime equal xy plus y. So xy prime equal xy plus y. I'm going to use separation of variables to show you that I indeed get the same exact equation. So y prime is dy over dx, so I get x dy over dx. I'm going to factor a y here, so this is x plus 1. Separate the variables, dy with y, dx with x. So I'm going to multiply dx on the right hand side and divide by x dx, and divide by y on the left. So this is dy over y. And now I'm going to integrate both sides. So integral of dy over y is ln y equal, I could split this into 1 plus 1 over x dx, which is x plus ln x. Okay, integral of 1 dx is x, integral of 1 over x dx is ln x plus c. Okay, and so I will get so y equal e raised to the right hand side, x plus ln x plus c, which I could write as e to the x times e to the ln x times e to the c. And e to the c is just another constant, yeah? So I would get here e to the ln x is just x, e to the x, and e to the c is a1. This is exactly what I was talking about when I said my constant of integration in the solution of the first order differential equation is the missing a1 that I either need boundary conditions or initial conditions to solve for. So this guy here is my a1. It's e to the c that I don't know, that I expressed everything with respect to that. Okay, now by looking at this final answer, someone naively may think that it's not the same as the answer I got first, except when you stop to think what this guy is. If I were to do a Maclaurin series expansion for e to the x, e to the x I'm not gonna do this in steps because I do have separate videos on how to deal with Taylor series and Maclaurin series, but I will go ahead and write the final answer for what that is for e to the x. You got e to the x, if you were to do a Maclaurin series expansion on this, get 1 plus x plus x squared over 2 factorial plus x3 over 3 factorial, etc., which is the same thing as the summation of x to the n over n factorial from n equals 0 to infinity. Okay, so if I plug that there for e to the x, notice I will get a1x x to the n over n factorial, right, from n equals 0 to infinity. Okay, or let's use k. Let's use k, because now in a second I will change the index. So this is gonna become looking directly at what I had originally, notice that if I factor out so this is here x k, so this is gonna become a1 x to the k plus 1 over k factorial. Okay, okay, so this, okay, if I go back to the red equation and I factor out an x, look what I get. So back to the original one, so if I factor out an x, oh, I hate going back and forth on this. So a1 x, and if I open bracket, the first term is 1, okay, and the second term is x over 1. Come on. And the third term is, if I'm factoring out an x, this would be x squared over 2 factorial, and this is x over 1 factorial, and this is 1 over 0 factorial. So you can see now the power of x matches the integer power of x matches the integer factorial in the denominator, and so etc. So this is enough to see that this is the same thing as right, I'm trying to show that it's the same as the green one. So this is going to be a1x, and then I get x to the k over k factorial, right? So and this is starting, so this series is here, and this is starting from k equals 0 to infinity. And if I now pull this x, right, group the x's together, I would get a1 x to the k plus 1 over k factorial times a1, right, which is the same exact answer I got in green from k equals 0 to infinity. So you could see that once you take care of that Maclaurin series expansion for e to the x, you do indeed get the same answer whether you solve using series method or elementary operation. So I hope this is a good illustration on how to apply or how to solve a differential equation using the series method. It's a little bit laborious, and intense in terms of the algebra, but it's not that difficult. The challenge is to be able to figure out a recursion formula or formulas, depending whether we're doing first order or second order or third order, to relate the coefficients of the differential equation with each other, such that knowing 1 or 2 or 3, you could figure out all the rest, and then plug them back into the assumed power solution series to figure out the final series solution of the differential equation. That summarizes. This is number 1 in section 12, in chapter 12, section 1.